Hi everyone! I am Erica May Piasoy, a third-year math major student of the Kapolong College of Agriculture, Sciences, and Technology. And for this video, join me as we talk about the applications of first-order linear differential equations. So, let's get started! The applications of first-order linear differential equation consists of first, Newton's law of cooling, second, laws of growth and decay, and third, orthogonal trajectories. But for this tutorial, we are only gonna tackle about the first and second applications, that is Newton's law of cooling and laws of growth and decay. For the first application, Newton's law of cooling states that the rate at which an object cools is proportional to the difference in temperature between the object and the object's surrounding. That is, we have the rate equation, the change in temperature with respect to time is equal to K, which is our proportionality constant, times T, which is the temperature of the substance, minus T sub m, which is the temperature of the medium. And in solving cases such as this, we use the general solution T is equal to T sub m plus C times e raised to kt. For example, a glass of hot water has an initial temperature 80 degrees Celsius placed in a room where the temperature is 30 degrees Celsius. After 1 minute, the water temperature drops to 70 degrees Celsius. What will be the temperature after 3 minutes, and at what time will the water cool down to 40 degrees Celsius? In order to solve this, we first have to get the values of C and K in order to proceed with solving the values of what is being asked in the problem. To solve for C, we use the initial temperature T is equal to 80 degrees Celsius at time 0, with the temperature of the surrounding T sub m is equal to 30 degrees Celsius. Using the general solution, T is equal to T sub m plus C times e raised to kt, we substitute these values in order to get AT is equal to 30 plus C e raised to k times 0. We leave C and K as they are because we are actually solving for their values in this step. Next, AT is equal to 30 plus C e raised to 0 because K times 0 is equal to 0. And then further simplifying, we get AT is equal to 30 plus C times 1 because e raised to 0 is equal to 1. And then by addition property of equality, AT minus 30 is equal to C, and thus we get the value of C, which is 50. After which, we use the other condition in order to solve for the value of K. That is, at time 1 minute, the temperature of the glass of hot water drops down to 70 degrees Celsius at the temperature of the surrounding T sub m is equal to 30 degrees Celsius. So using the general solution, T is equal to T sub m plus T e raised to kt, we substitute these values in order to get T, which is equal to 70, is equal to the temperature of the medium, which is equal to 30, plus C, which is equal to 50, that is what we have solved a while ago, times e raised to k times the time is equal to 1. Simplifying this, we use the addition property of equality to get 70 minus 30 is equal to 50 times e raised to k times 1. 70 minus 30 is equal to 40, which is equal to 50 times e raised to k. And dividing both sides by 50 in order to eliminate 50 on the right-hand side of the equation, we get 40 over 50 is equal to e raised to k. And getting the lowest term of 40 over 50, we get 4/5 is equal to e raised to k. And by loss of logarithm, we get ln of 4/5 is equal to ln of e raised to k. We do this in order to cancel out e on the right-hand side of the equation so that in the end, we may get k is equal to ln of 4/5. Finally solving the values of c and k, we now have our solution to the problem, that is t is equal to 30 plus 50, which is the value of c, times e raised to ln 4/5, which is the value of k, times t. Using this equation, we may be able to get the values of what are being asked in the problem. Now, the first question is, what will be the temperature after 3 minutes? Therefore, we are being asked of the value of the temperature. And using our obtained solution a while ago, we have t is equal to 30 plus 50e raised to ln of 4/5 times t. We substitute the value of time, that is 3 minutes, into our solution. Therefore, we get t is equal to 30 plus 50e raised to ln of 4/5 times 3. And by loss of logarithm, we can therefore get t is equal to 30 plus 50e raised to 3 ln of 4/5. And as we input this in our calculator, we get the value of time, t is equal to 55.6 degrees Celsius. As for the second question, we have, at what value of time will the temperature be 40 degrees Celsius? Again, using our solution, t is equal to 30 plus 50e raised to ln of 4/5 times t, we substitute the value of t, which is 40, in order to get 40 is equal to 30 plus 50e raised to ln of 4/5 times t. By addition property of equality, we get 40 minus 30 is equal to 50e raised to ln of 4/5 times t. Performing the operation on the left-hand side, we get 40 minus 30 is equal to 10, and on the right-hand side of the equation, we can write 50 times e raised to ln of 4/5 times t into 50 times e raised to t ln of 4/5 by loss of logarithm. And then, dividing both sides by 50, we get 10 over 50 is equal to e raised to t ln of 4/5. And obtaining the lowest term of 10 over 50, we get 1/5 is equal to e raised to t ln of 4/5. And again, by loss of logarithm, we can write it as 1/5 is equal to e raised to ln of 4/5 raised to t. By doing this, we can cancel out e raised to ln in order to get 1/5 is equal to 4/5 raised to t. And then, by loss of logarithm, we can write it as ln of 1/5 is equal to ln of 4/5 raised to t. We do this in order to get ln of 1/5 is equal to t times ln of 4/5. And finally, we get the value of t as equal to ln of 1/5 over ln of 4/5. And then, as we input this in our calculator, we get the value of t as approximately 7.2 minutes. Therefore, the temperature after 3 minutes will be 55.6 degrees Celsius, and the water will cool down to 40 degrees Celsius after about 7.2 minutes. Now, for our second application, the laws of growth and decay states that the rate at which a substance changes is proportional to the quantity of the substance present at any time. That is, we have the rate equation dx over dt is equal to kx. In solving problems such as this, we use the general solution x is equal to C times E raised to kt, where x is the quantity of substance present at any time, k being the proportionality constant, and t, which is equal to time. For example, a radioactive material has an initial mass of 100 milligrams. After 2 years, it is left to 75 milligrams. Find the amount of the material at any time and what is the period of its half-life. To do this, just like we did in the first application, we first have to solve for the values of C and K. Solving for C, we have x is equal to 100 milligrams at time 0. Using our general solution, x is equal to C times E raised to kt, we substitute the given values so that we get 100 is equal to C times E raised to k times 0. And knowing that k times 0 is equal to 0, we get 100 is equal to C times E raised to 0. Also, because E raised to 0 is equal to 1, we get 100 is equal to C times 1. And finally, we get the value of C, which is equal to 100. And now, solving for the value of K, we have x is equal to 75 milligrams after T is equal to 2 years. Using our general solution, we have x is equal to C times E raised to kt. We substitute the values of x and t into the equation. Thus, we get 75 is equal to 100, which is the value of C, times E raised to k times 2. Dividing both sides by 100, we get 75 over 100 is equal to E raised to k times 2. Obtaining the lowest term of 75 over 100, we get 3/4 is equal to E raised to 2k. By laws of logarithm, we can write this as ln of 3/4 is equal to ln E raised to 2k. We do this in order to cancel out ln E on the right-hand side of the equation to get ln of 3/4 is equal to 2k. And then, dividing both sides by 2, we get k is equal to 1/2 ln of 3/4. Thus, we have the value of the substance present at any time as x is equal to 100 E raised to 1/2 ln of 3/4 multiplied to t. And then, for the question, what is the period of its half-life, we are being asked the value of time if the amount of the initial substance is reduced to a half. Therefore, we multiply 1/2 and 100 in order to get the value of x, which is equal to 50 milligrams. Using our obtained solution, that is x is equal to 100 times E raised to 1/2 ln of 3/4 times t, we substitute the value of x in order to get 50 is equal to 100 times E raised to 1/2 ln of 3/4 times t. And then, dividing both sides of the equation by 100, we get 50 over 100 is equal to E raised to 1/2 ln of 3/4 times t. Further, on the left-hand side of the equation, we obtain the lowest term of 50 over 100 as 1/2, and on the right-hand side of the equation, we multiply t to 1/2 in order to get E raised to t over 2 times ln of 3/4. By laws of logarithm, we can write this as 1/2 is equal to E raised to ln of 3/4 raised to t over 2. By doing this, we can cancel out E raised to ln in order to get 1/2 is equal to 3/4 raised to t over 2. Again, by laws of logarithm, we can write this as ln of 1/2 is equal to ln of 3/4 raised to t over 2. By doing this, we are able to write it as ln of 1/2 is equal to t over 2 times ln of 3/4. And then, multiplying both sides of the equation by 2, we get 2 times ln of 1/2 is equal to t times ln of 3/4. To finally solve for the value of t, we divide both sides of the equation by ln of 3/4 in order to get t is equal to 2 times ln of 1/2 over ln of 3/4. As we input this in our calculator, we get t is approximately 4.82 years. Therefore, the amount of the material at any time is x is equal to 100 times e raised to 1/2 ln of 3/4 times t, and the period of its half-life is approximately 4.82 years. And that's it for this video. I do hope that you've been enlightened in terms of this topic, and let's see each other in my next videos.